Quorum. Okay, so everybody, to welcome you to the last non-commutative geometry and topology seminar of the year. Today's speaker is Marco Matassa from Oslo Metropolitan University, and he will speak about Fubini-Study metrics and Levi-Civita connections on quantum projective spaces. So,
thanks, Ray, for the introduction. It's a pleasure to talk in this seminar, formerly, somehow based in Prague, even though we are kind of spread out. Okay, let me share my screen. Okay. So hopefully it works for everyone, otherwise just send me a message. Okay, yeah, so you heard the title. So I think my first job is to start by kind of giving an overview of what it is that I'm trying to accomplish, or even how to make sense of these words in this quantum or non-commutative context. And I will also discuss a little bit the kind of framework that I will be working on. Of course, there can be many different choices, and this is just one possible one. So I think it goes without saying that metrics and connection are somehow the cornerstones of differential geometry. It's hard to do without that. So it's certainly desirable to extend this notion to quantum spaces. So what we mean by quantum spaces, of course, depending on your taste, let's say. So roughly speaking, would be some class of algebras, non-commutative ones, that somehow will encode some sort of quantization process. Let me be very vague here. In particular, for me, I will mainly care about example coming from the theory of compact quantum groups, and particularly the homogeneous spaces. I will say more about that later on. So, of course, there are different possible approaches to this problem, as I was just saying. So maybe let me just start by briefly mentioning one of them that actually I'm not going to use at all in this talk, but just to say what are some of the possibilities. For instance, one could consider the theory of compact quantum metric spaces developed by Riffel following ideas of Kohn. And somehow in this theory, one looks at semi-norms on the state space of a certain algebra. And this, at the end of the day, leads to a quantization of the metric in the sense of the distance between points. In this setting, for instance, points in the classical setting are seen as pure states on the state space. Okay, so in a sense, it really quantizes the distance. But what I want to consider here for the purpose of this talk is some framework where we can really talk about the metric tensor, not just the distance between points. Especially because I want to explore the compatibility between this sort of metric tensor and then connections that we're going to introduce. So it is really important that we have this sort of tensors at our disposal. So for this reason, I will consider somehow a more algebraic approach, let's put it this way, which, for instance, you can find explaining in quite some detail in the recent book by Beggs and Majid. Of course, many of these ideas have been around for a long time by now, but if you want just one place where you can read about essentially all these things, I would recommend taking a look at this book. So let me then start by reviewing a little bit what are the main ingredients and somehow the main characters in this story. So we have then, at least for this first part, A denote a general associative algebra, non-commutative, let's say, which we think of as the function of our non-commutative space, our quantum space. So then the first thing we want to introduce is some sort of notion of differential structure, smooth structure, let's say. And the way we proceed here is by introducing a differential calculus on this algebra, which perhaps looks a little bit strange from the point of view of smooth manifolds and so on, from the classical point of view of differential geometry, but it is a reasonable starting point, let's say. So these are more or less standard notions. So a differential calculus over an algebra A is simply a differential graded algebra. So we have a graded derivation D, such that the zero form are simply the function, so the algebra itself, and then it is generated in degrees 0 and 1. Okay. So in practice, all that we care in most cases is not the full calculus, but just the first order part. So this we are going to call first order differential calculus and abbreviate as FODC. So it's simply then crystallizing this notion of what happens in degree 1. So we have a bimodule, omega, with a derivation, so a linear map D, which obeys the Leibniz rule in the following sense. And such that omega is generated as a left A module, say, by these elements dA. So in a sense, this contains the essential information about the differential calculus. And in particular, given any such first-order differential calculus, it turns out that there is a universal object that we call the universal differential calculus, such that its degree 1 part is exactly this first-order part, and then any other differential calculus can be obtained as a quotient of this one. So it's a very flexible notion. So for the purpose of this talk, I will mainly talk about just and consider the first-order part. In a sense, that's where the essential information is contained. Okay, then moving on, we would like to introduce a notion of quantum metric. So again, here there's many possible choices. So the one that I'm going to use is the definition that was introduced by Beggs and Majid in 2014. So a quantum metric in this sense is an element G in the tensor product of one form with one forms over the algebra A, which crucially is required to be invertible, and which of course is trying to capture the classical invertibility of the metric tensor in the standard setting. So invertibility here means the following thing. We require that there exists a bimodule map, denoted by these brackets, again from the same tensor product to the algebra A itself, such that the following identities are satisfied. Where here we use this notation G1, 2 for simply the two legs of the metric tensor. So this maybe looks a little bit abstract, and indeed it could be very economically phrased by saying that this is essentially saying that omega 1, this first-order differential calculus, becomes an invertible object in the category of A bimodules. So it's probably a very highbrow point of view, but let me just mention it. And it turns out that it's actually quite a strong requirement, no? Ray is shaking. I think it's correct.
Invertible, because if it was invertible, then it would be an isomorphism. It's a question of terminology. If it was an isomorphism, sorry, if it was invertible, it would be an isomorphism, which is not.
Maybe we can discuss that later.
Okay, sure.
Anyway, let's say
not important.
Yeah, it's not important anyway. Just in any case, let me stress that this is actually a very strong notion, and indeed there are some other variants of this notion that are a bit weaker. Particularly, you can say this is a very strong notion because if you have a quantum metric in this sense, then it turns out that it's automatically central. So this 2 tensor is going to commute with all elements A in your algebra, which might not be necessarily the case for a generic algebra that you want to consider. And of course, in the classical case, the metric tensor is also symmetric. And so we would like to have an analog of that. So we say that a quantum metric in this sense is symmetric if after applying the wedge product, so here wedge is simply the product in our differential graded algebra, so something that goes from 1 forms to 2 forms, if this map applied to the metric tensor gives 0. Okay, so this is one way to capture classically the fact that you have a symmetric 2 tensor. So this is definitely an extra property that we want to require if possible. Okay, next, again, some very general notions, and I think this one is more familiar, is the notion of connection on a module. And it's quite standard. So here in this definition, I talk about left connections, and then later on, I'm just going to forget about left and simply say connection. Of course, there is an analog right version. So a left connection on a left A module E is a linear map that obeys the left Leibniz rule, which is exactly what you would expect. So here you have the connection, and then the multiplication of A with an element E in your module then gives the following identity. Where here on this factor, we use a differential, which is part of our, let's say, differential calculus structure. Okay, so this is true for any left module E. So in particular, we can look at the case where E is the 1 forms itself. In that case, we can require further properties of this connection. So in particular, we can introduce the notion of torsion, which somehow is trying to capture exactly torsion in the classical sense, except that here you have to keep in mind that somehow, in a sense, everything is dualized. So typically in the classical setting, we would talk about connections on the tangent bundle, but here what we are doing for various reasons is to work with the cotangent bundle, which turns out to be somehow more natural for most examples. So the torsion of such a connection there is the left A module map, which is defined by the following identity. So again, it might look a little bit different from the usual way you would define torsion of a connection, But this is simply because we are dualizing everything and looking at it from the point of view of the cotangent bundle. And then we say that a connection is torsion-free if this map is identically zero. Okay. Okay, next we have a notion which is a little bit more unfamiliar and is trying to capture some sort of compatibility between a connection and a quantum metric in the previous sense. So suppose that we have such a quantum metric G, we introduce this notion of cotorsion, which is due to Majid. So it is defined as follows. The cotorsion of a connection with respect to a quantum metric G is an element that I denote by co-t nabla, defined by this somehow kind of unfamiliar expression, which observe that crucially contains the quantum metric G. So it's going to be some operation applied to this quantum metric. We say that a connection is cotorsion-free if this element is identically zero. So this is fairly mysterious, I think. So let me show you a little bit in an example what happens in the classical case and what kind of property it is trying to capture. So let's say then we have a connection nabla on a manifold with metric G. So a connection in the usual sense, that is on the tangent bundle taking vectors to vector fields, let's say. So we can define then another connection denoted by nabla star, essentially by forcing that the condition of metric compatibility is satisfied. So here, if you forget about this star for a moment, this will exactly be the condition that metric compatible connection satisfies with respect to the metric G. Okay, but here we take this as defining this new connection, nabla star. And then it turns out, once you dualize everything, as I mentioned, that the cotorsion of nabla, defined in this sense, coincides with the torsion of this other connection that is defined in terms of that. So somehow this is part of some general ideas developed by Majid about some sort of self-duality. Well, I definitely don't want to get into that. So concretely what it means in this, let's say, commutative example, is that if we have a connection which is torsion-free and cotorsion-free, this means that the covariant derivative of the metric, which is a 3-tensor, then essentially becomes symmetric in the first two slots. So as you can see in this identity here, you can swap x with y, and here x, y, and z are vector fields. So again, these are connections in the usual classical sense. And so this identity is satisfied. And you can see that this is really a weaker notion than metric compatibility, which will require that the covariant derivative of the metric itself is zero. While here we mainly require this symmetric property. So it is a weaker version of metric compatibility. Okay, so then in the classical case, the Levi-Civita connection is the unique connection on the tangent bundle, say, of a smooth manifold, which is torsion-free and compatible with the metric. Okay, so this motivates the following definition. We say that a weak quantum Levi-Civita connection is a connection in the previous sense, so that is defined in terms of this differential calculus on A, which is torsion-free and cotorsion-free. So, as I just said, this cotorsion-free is a weak property of metric compatibility. So, strictly speaking, this notion here does not really capture the classical property of the metric, of the Levi-Civita connection. So, if you specialize this definition to the classical case, then you could get something more general. So somehow this is why we have this weak in front of this name. Okay. So of course it would be desirable to also define a sort of strong version of this definition that really captures the proper metric compatibility as in the classical case. So the drawback is that if we want to require that, we need an extra assumption. And this will be that of having a bimodule connection, which is a notion that I'm going to recall in a moment. So first, let me try to motivate why it is desirable to have this extra property of having a bimodule connection. So in the classical case, if you have a connection on a module, for instance, on the one form, then this naturally extends to a connection on the tensor product, say, of such forms. Connection on modules then naturally extends to connection of the tensor product of these modules. Now, in the quantum case, this is not guaranteed. You don't get this for free. you need to assume more about your connection. And a connection might not satisfy this property. And I would say, in a sense, the connection that satisfy this sort of lifting are actually quite rare. So this motivates then this definition. We say that a left connection is a left bimodule connection on now a bimodule E if we have a bimodule map sigma E, which somehow generalizes the flip. So you simply should think about flipping the two tensor factors, such that essentially we also have a right version of the Leibniz rule. Okay, so you will multiply them by elements from the right, and then you need to flip the elements if you want to have your one forms to the left, essentially. And again, in the classical case, any connection is a bimodule connection simply by using the flip. So you get this for free. Should also be mentioned that this bimodule map, which is sometimes called the generalized braiding, is not additional data for the connection, but it is uniquely determined by this condition above whenever it exists. So it's not something you have to introduce extra. So a connection is either a bimodule connection or not. Okay, so then if you have a bimodule connection, then you can prove that then your original connection can be extended to a connection on this tensor product, essentially by using the Leibniz rule and this generalized braiding. So in a sense, this is the main property of these bimodule connections. Okay, so in particular, then we can look at this quantum metric, as I explained before, which is, lives in this tensor product of one forms over the algebra. And then the extended connection applied to this element is simply obtained, as I said, by acting with the connection on the two legs of the metric, and then flipping the elements in the second factor by using this generalized braiding. Okay, then if we have then this extra property of being a bimodule connection, then we can naturally propose the following definition. We say that a bimodule connection is quantum metric compatible with a quantum metric if the connection applied to G, that is this extended connection now, is zero. Okay, so again, this is the analog of the covariant derivative of the metric being equal to zero, which is one of the ways to formulate metric compatibility in the classical case. Okay, so then if we have also this stronger version, we can then formulate a definition of quantum Levi-Civita connection, which is then really the classical analog. In this case, we want to have a connection, which is a bimodule connection, and then it should be torsion-free and quantum metric compatible with the metric. So somehow these are a lot of things to really ask for. And if you take a generic example, this sort of properties might not be satisfied. So one might look for certain relaxation of these axioms, let's say. Also, let me add one more remark. So as I said, in the classical case, this cotorsion freeness is really a weaker property. And one would like this to be the case also in the quantum case, but strictly speaking, this is not the case. That is, this notion of being cotorsion free and being quantum metric compatible, they are not always comparable notions. They are if you also add an extra assumption, which is the following property here, that the composition of the wedge product with sigma plus the identity map is identically equal to zero. So of course, this property is always satisfied in the classical case where the sigma is simply the flip map. And in this case, then, if you have this property also generally in the quantum case, then you can show that there is the following relation between this cotorsion element and the wedge product applied to the first leg of the covariant derivative of the metric. So that you can see that with this extra assumption, being cotorsion free is actually a weaker property than being metric compatible. Okay, but let's say it's not guaranteed that this extra property is going to hold also. So one perhaps might want to check these two things separately in examples, let's say. Okay, so I think that's a lot of definitions, but I think many of them somehow are quite intuitive or make sense. It's just somehow trying to translate what happens in the classical case in a way that is as close as possible. And in a sense, the main thing is really trying to dualize everything and formulate things from the point of view of the cotangent bundle. That is from the point of view of differential calculus. So that's nice and all, but then what are examples that satisfy all these properties, let's say? Well, there are certain examples, and many of them are described in this book by Bex and Majid that I mentioned. But it must be said that there's not many examples coming from the theory of compact quantum groups. Okay, and that, in a sense, is the main thing I'm interested in, particularly in the case of homogeneous spaces. Essentially, there is one example which has been treated in quite some detail with most of these properties that I mentioned, and this is the case of the quantum to sphere, which in a sense is the easiest possible example of a homogeneous space coming from a compact quantum group. And so this example was discussed by Majid in 2005, and among other things, he proves that we have a quantum metric, but I should point out actually without this invertibility property. So somehow this notion of having a quantum metric in that sense came later on. Yeah, let me just say that. And then he proves that there is a weak quantum Levi-Civita connection, so a connection which is torsion-free and cotorsion-free, but he did not prove whether this connection was a bimodule connection and then it is strongly compatible with the metric in the sense I just discussed. So in a sense, even in this particular case, there are somehow some partial results that one would like to extend. And so what I want to talk about today is generalization and also an extension of this result by Majid to general quantum projective spaces, of which, of course, the quantum to sphere is just the simplest example. And moreover, I conjecture that this result that I'm going to present are going to hold more generally for the class of quantum irreducible flag manifolds, of which the projective spaces are, in a sense, the main example. Okay, so then I guess let me move on to these flag manifolds. I will recall some facts about them, not in any great detail. The main point, let me say, is that there's going to be a lot of structural similarities between projective spaces and this more general setting. And in particular, there are some general results available for this whole class. And so one might as well just try to state everything in this more general setting and then only reduce to the projective spaces when necessary. Somehow with an eye towards generalization. Okay, so then let me start a little bit classically then. A generalized flag manifold is a homogeneous space of a particular type, of the type, let's say, G mod PS, where G is a complex simple Lie group, or semi-simple if you like, and PS is a parabolic subgroup. So if you know what, let's say, especially parabolic subgroup means, that's great. If not, it's not somehow that important here for the purpose of this talk. You might notice that there is this subscript S here, and this is because these subgroups actually turn out to be in one-to-one correspondence with subsets of the simple roots of the Lie algebra corresponding to the Lie group. And there is a recipe that somehow produces them concretely out of this Lie algebraic data. It's a nice class of homogeneous spaces. They can also be formulated in terms of the compact real form that I'm going to denote by U. And in this case, we take the quotient by this other subgroup that I write as Ks, which just for some terminology is called the compact form of the Levi factor. Again, the details are not really that important here. It's just some sort of notation that you might see later on in the quantum case. Okay, so these are some of them general flag manifolds. Of particular interest is the case of irreducible ones. So there's a long list of equivalent criteria that you can use to define what irreducibility means in this case. I'm just going to state two of them. So one, I think it's very intuitive because irreducibility and being a simple module are more or less synonymous, you could say. So you look essentially at the tangent space of such a homogeneous space, G mod PS, and you ask that this is a simple module with respect to the Lie algebra PS. So this is a sort of transparent definition, but perhaps it's not the easiest one to work in practice. And there is this second condition, which is definitely more obscure, I think, but in practice it is extremely useful. And it gives a characterization in terms of the subset S, as I mentioned above. You take all the simple roots and you remove just one that I'm going to denote by alpha S. This simple root that you remove must have the property that it appears with multiplicity 1 in the highest root of the Lie algebra. So again, this might seem a bit obscure, but it's quite concrete to work in practice. In particular, using the second criterion, you can immediately classify all these irreducible flag manifolds just by looking at highest roots and checking coefficients. Okay, so then let's move on to the quantum case. Again, I will not give too many details also because in a sense,
Marco,
yes.
sorry, I have a quick question on these two conditions.
Yeah.
Can you go back to the conditions?
Yeah.
Is this equivalent to have the K as the same rank as G?
Yeah. I'm not sure if it's enough, but they definitely need to have the same.
Yeah, rank. I know they have. I know because these two conditions are verified when K is the same rank as G. I was wondering if it is equivalent.
I'm not sure. I'm not sure.
Yeah, do they always have a complex structure, these things?
Yeah, they're all color manifolds in particular.
Okay, great. Then it is equivalent. Sorry for the question. Thank you.
So for instance, another condition is that you have a billion nil radical. That's also an equivalent condition. So as I said, there is a long list now. Somehow these two are the ones that I'm more familiar with, I must say. Yeah, so
you mentioned projective space is a special case of this. Then
yes.
Then which case is it?
Yeah, I'm going to mention this in a second. So
sure.
Just a little patience. Yeah, I'm going to say this in a second. Okay, so moving on to the quantum case, then again, cutting a sort of long story short, one convenient starting point to phrase this whole story is to start from the quantized enveloping algebra, which I guess that many of you that are here today are familiar with. If not, let me just say that it's some sort of Hopf algebraic deformation of the universal enveloping algebra of the Lie algebra U. So in particular, it has some generators that I denote by K, E, and F with some relation, very explicit, and with Hopf algebra structure and so on. Again, details are not so important here. Okay, so then within this somehow quantization of the enveloping algebra, it is very easy to define an analog of the Levi factor, which is what I wrote before as Ks. This goes back to Stockman and Dijkhuizen, and they introduced this very simple quantization as a Hopf star subalgebra of this quantized enveloping algebra in a very simple way. All you do is you retain all the generators K, which somehow is the Cartan part of this quantized enveloping algebra. And then for the E and F generators, which somehow are the root vectors corresponding to the simple roots, you only take those J that belong to the subset that defines the parabolic subgroup. And you take the algebra generated by these elements. It's very easy to check that it's a Hopf star subalgebra. So it's a very easy quantization of this object within this setting. Okay, then what about quantum spaces? Well, then one just has to think a little bit dually. And in a sense, we have this quantized coordinate ring that I denote by CQU, which can be defined in a sense as the restricted dual Hopf algebra of this UQU. So very concretely, sorry, you look at the matrix coefficients of finite dimensional representation of this algebra, UQU. And actually, it turns out that the representation of this quantized enveloping algebra are essentially the same as in the classical case. You have some extra ones that you usually disregard, but otherwise they can be put in one-to-one correspondence with the classical one. So again, you have highest weights and all that. The representation theory is pretty much as in the classical case. Okay, then you can define then, and again, this CQU is what you should think as the functions on this quantum space. So this algebra now will be non-commutative, and somehow that's why we consider it as a quantum space. Okay, then quantum flag manifolds can be defined in this sense by simply looking at all the elements that are invariant under the action of this quantized Levi factor. Again, we have an action of this quantized enveloping algebra on the quantized coordinate ring. somehow simply by duality in a sense. And this lets us define these homogeneous spaces. Just a word maybe for the more expert of you. So these are very easy type of quantum homogeneous spaces. In particular, these are those coming from a quantum subgroup. So you might as well, for instance, introduce these spaces using coactions and all that. In a sense, it's really simple example of quantum homogeneous spaces. Okay, anyway, they're concrete algebras, and it turns out that there is a very nice and easy, at least relatively speaking, presentation, which is completely uniform for all these, actually not even irreducible, just quantized flag manifolds, which is due to Heckenberger and Kolb in terms of some generators and relations. So in a sense, then you can kind of forget maybe exactly where they come from, all these compact quantum groups and so on, and simply work concretely with these algebras, with these generators and relations. So that's more or less the point of view that I'm going to adopt here in this talk. So again, I'm not going to say anything very explicit, but let me just say that, for instance, in the reducible case, these quantum flag manifolds that in the following I'm going to denote with this calligraphic B, well, it has certain generators that I denote by Pij, where these ij go from 1 to n, and this n is simply then the dimension of a particular representation, which it has highest weight omega s, where s is this index that corresponds to the simple root that you remove. Okay, it turns out this is somehow a general construction that is related to a projective realization of these spaces. But again, I will not say anything about that. So we have certain generators, and moreover, you should think about these generators as being entries of a projection. And again, this also in the quantum case. And moreover, this projection can be made orthogonal by making appropriate choices. Again, not very important here. And it turns out that these are projections that has quantum rank 1 in a certain sense. I'm going to say a little bit more about that later on. Okay, so now coming back to the quantum projective spaces, which somehow disappear from the picture up to now. So classical projective spaces and then quantum projective spaces within this setting are then a special case of this general construction. All you do is that you look at the Lie algebra of type A, so let's say SUN, say if you look at compact real forms, and what you want to do then, as I said, there is a single simple root that you remove from this construction, and the simple root you remove for the case of projective spaces is either the first or the last node of the Dynkin diagram. And actually, you could also remove something in the middle, and that more generally would correspond to Grassmannians. So these are also then more complicated, let's say, examples of irreducible flag manifolds. Okay, so these are very simple condition that then captures the projective spaces within this general description. And even to be a bit more concrete, and then, because I think it's a bit, of course, fairly abstract if you've not seen these things before, just to have something concrete in mind, let me say something about the classical, let's say, limit of this description in the case of projective spaces. So these elements Pij, these entries of this projection, can be seen then as function on the projective spaces, particularly this function here, which are defined in terms of the usual coordinates Zi in the usual realization of projective spaces within the complex space of dimension r+1. So you simply take then the coordinate Z, the complex conjugate, and divide by the norm of this element. It is not obvious somehow to see that the quantum description leads to this, but that is something that indeed holds. And let's say within the classical case, you can easily see that indeed these are entries of a projection, just by somehow summing the elements, and also that it has rank 1, because you get that the trace of this projection is 1. Okay, so maybe you might be asking, why irreducible flag manifolds? Why should we care about them? Perhaps they might look a bit exotic. Well, the point of view here is that they're actually, in a sense, the nicest possible quantum spaces that you can consider. which is perhaps not obvious at first, but it turns out to be the case due to a series of nice structural properties. In particular, these quantum spaces, they turn out to admit canonical differential calculi. And these are a very important result of Heckenberger and Kolb. So in a series of 2 papers from 04 and 06. So again, I will not say so much about this, but let me just say that, for instance, they consider and completely classify all the irreducible and covariant first-order differential calculi over these quantum spaces. Again, I'm not really going to define what these words mean, but let's say some natural condition to impose on such a quantum space. Once you put these 2 extra conditions, then it turns out that there's only 2 possibilities. And these classically turn out to correspond to the holomorphic and anti-holomorphic part of the differential calculus. And these 2 differential calculi, in this quantum case, I will denote by omega plus and omega minus. And in particular, we look then at the direct sum, which will be essentially the quantization of the complexified cotangent bundle in the classic case. So this is the kind of object that I'm looking at now. So also these differential calculi, they have a very concrete description in terms of generator and relation, again, due to Heckenberger and Kolb. And in the following, I'm going to write the generators as delta Pij for the holomorphic part and del bar Pij for the anti-holomorphic part. And I'm going to briefly show you some of the relation in the projective space case. Okay, so I would like to say something then about these relations. Again, not going very deeply into them and only somehow to have an idea, because I'm going to show you some formula, but no proofs or anything complicated. And I think the most convenient way to state this result and to write down this formula is to use a little bit of categorical language. So essentially, what we're looking in this kind of description is the category of finite dimensional representation of this quantized enveloping algebra. And this category has the property of being monoidal, which means that we have tensor product. It is rigid in the sense that it has dual objects. And it is braided, so it has an analog of the flip map satisfying certain properties. So I'm not going to recall most of these properties, but just maybe a little bit of notation. Then the braiding, which is what generalizes the flip map in the classical case, is written as R hat for objects V and W, so modules. And duality in this category is encoded by certain morphisms that are called the evaluation and co-evaluation morphism that need to satisfy certain conditions that somehow express duality. And you might notice that there's 2 sets of them, so E, C, and E prime, C prime. This is because in general, we talk about left duals and right duals. And in a general category with this extra structure, these are 2 separate things. Actually, in the case of UQG, the 2 objects can be identified, but with a little bit of care. So for most purposes, it's actually better to keep them separate and simply write this morphism as 2 separate entities. Also, I'm not writing here somehow the object on which this morphism acting, because in the following, I will just focus on one simple module that I will simply denote by V. And this is exactly this module V omega S that appears somehow in the construction of these generators for the irreducible flat manifolds. Okay, so that's the only somehow representation that we want to look at. Let's say the one and its dual, really. Okay. Just a little bit more notation, but it's really not important. You can kind of forget about this immediately just because I'm going to employ this in some formula. And maybe it's just a kind of advertisement for some of the more expert among you on these things, because I'm going to use these maps that I write as S that are certain combination of the braiding. So you should really think about this as certain flip maps. And the only way I'm writing this down here, because this is a somewhat different description for what Heckenberger and Kolb do. And I think that for most purposes is a bit more convenient. So let's say in my paper, I use this equivalent, but I think more convenient description. Let's say just to see what they look like in the classical limit, these are some sort of flips let's say you have an object with 4 indices, and then you just flip some of these indices in a certain way. Okay, again, the details are not important. Similarly, we have a map T, which is the composition of these two maps, and this simply flips the first 2 indices with the second 2. Again, some analog of flip maps, but if you were to write explicitly this down in the quantum case, they would be extremely messy, okay? Because the braiding is sort of a complicated object, and writing it down is really bad. So that's why you kind of want to think about these sort of things in a very general way, using the categorical framework as much as possible. Maybe for projective spaces, it's still okay to write things down concretely, but if you plan to generalize, there's no hope of writing things down concretely. Okay, but so let me simplify things a little bit and then consider the case of quantum projective spaces. So in this case, it turns out that the braiding, so this analog, the flip map, also satisfies an extra property, namely a quadratic relation. Of course, the flip map always satisfies a quadratic relation, but a general braiding will not satisfy such a relation. Maybe it will be higher order. So in a sense, the projective space is the simplest case somehow because of this condition, one could say, really. It is also known as the Hecke condition for other reasons. Okay, so let me then show you what the relations are in this quantum projective space algebra. So I'm going to employ some index-free notation. And you should think about these generators P as having 2 indices, as I wrote before, so that this product of P and P has 4 different indices. And then what you're doing here, say on the left-hand side with this action of S, is to do some sort of flip of these indices. Of course, in the quantum case, it's not really a flip, but it's a very complicated operation that involves the braiding. And the outcome of doing this operation then is simply a factor, and then you get the same element. Similarly for S tilde, and then we have the action of one of these evaluation morphisms acting on P that gives a multiple of the identity. So somehow this is this quantum rank 1 condition that I mentioned before. Let me show the analog of this relation.
Can I? So you're the P here without any subscript, this is the matrix consisting of the generators.
Yeah, so here is not the matrix, but you should think that it's really the entries. I'm not writing the indices I, J, K, L. Okay, and then this S is acting on those indices.
Okay.
Okay. There's also an extra subtlety that one has to do everything dually, so there is a hidden transpose, but let's not get there. I mean,
thanks.
Yeah, but you see, it's a very somehow condensed and you know, they look very easy, this relation. If you were to write them down, they would be extremely messy. It's a bit hard somehow to get used to this sort of notation, perhaps, but once you get it down, it's actually very easy to work with. And this is actually pretty much what Heckenberger and Cobb do in their papers, by the way. Yeah.
So let me ask you, Marco, sorry, but let me ask you. So you don't want in the classical case they commute. There is no commuting relation in the classical case.
Actually, if you combine this first relation with the second relation, they give commutativity.
Oh, I see. Okay.
Yeah.
Thank you.
That's a very good point. Because essentially the first relation tells you that you can flip the first 2 indices, and the second relation tells you that you can flip the second 2 indices. So if you combine the 2, then you move an element Pij past an element Pkl. So that gives commutativity. Yeah, so these are the first 2 relations. And then the third relation is really, then I said, the rank 1 condition. So when you sum the diagonal entries of this projection, you get 1. And here somehow this, let's say, trace is a little bit more complicated, and it involves this, let's say, evaluation morphism. But you should think about it as a rank 1 condition, let's say, for this projection. Okay, so these are kind of nice relation, I feel. I said, once one gets used to this kind of notation. And then there is a similar description also for the differential calculus. Again, let me go very quickly here. The relation, they look very similar. Again, we have the action of these maps S and then S tilde on this combination P del P and P del bar P. So for the holomorphic and anti-holomorphic part. And then we have this relation for, let's say, You simply apply then the differential to the rank 1 condition, and this leads to this other condition here in the second line. Okay, and finally the right module structure, again, of course, classically everything commutes, so you don't need to specify that, but here in the quantum case, that's really important. This right B module structure is expressed in terms of this map T, which is simply the composition of S and S tilde. And again, don't bother too much about the details, just to give a little bit of a flavor of what goes on here. Again, let's say in the classical case, then the relation looks as follows. So again, you have this sort of relation that let you flip either the first two indices or the second two indices. And by the way, this is a relation that one can easily prove if one uses the local description of Pij as Zi Z by Zj bar divided by the norm. So they can also all be checked locally. So of course, maybe using this P is not the most obvious way to describe projective space in the classical case, but it's definitely a legitimate choice. Okay, so finally, let me say something about the results. So let's start then with quantum metrics. So classically, in a sense, most natural metric that you can introduce on projective space is the Fubini-Study metric. Usually this is introduced somehow by local formulae in terms of the coordinate Z and Z bar that I mentioned before, but you can actually check that the metric tensor can be somehow written globally in terms of this function P, using this holomorphic, anti-holomorphic differential, and then the Fubini-Study metric takes the following form. So again, it looks a little bit unfamiliar perhaps, but you can check that indeed is what gives the Fubini-Study metric in the classical case. So then this formula in a sense then is the starting point if you want to have an analog of that in the quantum case. So you simply try to translate as much as possible this expression here using the ingredient that you have in the quantum case. So as a quantum counterpart, then we take this element where essentially we replace these sums in I and J by this evaluation. And notice there is a small subtlety that is not just one of them, but you have to somehow use both of them in the right order. Again, there's some very good reason for doing that, but in, let's say, first approximation is just replacing sums with appropriate analog of sums in the quantum case. Okay, so then the expression looks very similar, especially if you write it down, let's say, using indices. Okay, then we have, first of all, the following result. We have the G is symmetric in the previous sense, so that if we apply the wedge product, which, by the way, let me stress, is not just anti-symmetrizing element. It's a very complicated product that is part of the structure of the differential calculus. Okay, so G is symmetric in this general sense and also real, which is not a notion I introduced, but it's an extra property. Also, we have these identities for G and differential in our differential calculus, which are really somehow the part of the color identities for a color metric. Okay, so the application of the differential on the first leg or the second leg of the metric G gives 0. And actually, these are very general results, and they hold not just for the quantum projective spaces, but for any quantum irreducible flag manifold. And these in particular are counterparts of the Kähler form that I introduced recently, using the definition that was introduced by Ray. So you could actually start from this Kähler form and completely obtain the quantum matrix in this way. But you can also somehow start from scratch by looking at it from this point of view. Okay, so let's say these results are completely general. You don't need to assume that you're in the projective space case. But for the next result, I really want to make this extra assumption. So for the case of quantum projective spaces, moreover, we have the following result. We have that G, as defined by the previous expression, is a quantum metric in the sense of Beggs and Majid. So recall this means that we need to introduce a bimodule map such that the following identities hold. Okay? And okay, so this is something one has to work quite a bit somehow to obtain. First of all, to somehow kind of find a natural candidate for what the inverse metric that is this bimodule map should be. Yeah.
Marco, the connection here went. Could you go back like 2 minutes?
Yeah. This one.
Yeah, just to the proposition. That's where it went.
Yeah. Yeah, you froze. Sorry, did you have a question about that or just to see it?
No. Just to go back, literally, when you mentioned scalar, the computer crashed. So.
Oh, okay, yeah. Well, I just said that, of course, one could start from those scalar forms and obtain the metric in this sense, also in that way. As I said, this sort of color form is, let's say, according to your definition, that kind of stuff. Yeah. As I said, then I want to assume that I'm in the quantum projective space somehow to check this invertibility condition, okay? And in this case, then I need to introduce this bimodule map. So first of all, I need to check, to really define a bimodule map. So check the properties of, that it preserves the relation in this differential calculus, A. And it turns out that the thing that works is something which is defined in the following way. Again, the particular expressions are not important. I'm just briefly flashing them at you to show that they include some, let's say, natural ingredient, which are in particular the co-evaluation morphism. So these are the C and C prime that act in the appropriate legs. And then some factors, okay? And just again, to keep the parallel with the classical case, then what this bimodule map here reduced to is then the following expression for this element P. So of course, we only have non-zero pairings between holomorphic and anti-holomorphic, and then we have concretely this kind of expression. So again, these are, let's say, conditions that one could check concretely using the local description in the classical case, but it would definitely not be the natural way to look at that, let's say. But here we have no alternative. I guess I must say in the quantum case, we can only really work with global objects, okay? So we formulate everything in terms of this del P, del bar P, and so on. Okay, so indeed there is such a bimodule map, and one checks that these identities are satisfied. So we have a quantum metric in this case. So if one tries to generalize, let's say, this inverse metric to the other irreducible flat manifolds, then you should expect that the expression should be more complicated for various reasons, okay? So you will not get the same formula as for the metric itself. Okay, so this is one result, first of all. So next, we have connections on this first order differential calculi, omega plus and omega minus. And again, these are given explicitly by the following concrete formula, which involves somehow this sort of flip maps, the T, and then the quantum metric, G plus minus and G minus plus, which are simply somehow the plus minus component of the metric and the minus plus. Okay, I guess I don't want to say much more about this. Yeah, sorry.
Will these guys be co-module maps with respect to the right OQ of SUN?
Yeah, they are, although I did not include this in the paper. Maybe I'm planning to write that at some point, I suppose, but they are. I'm going to say something more about this.
Because then they're going to be, they're the unique connections, basically.
Yeah. I'm going to say this in a moment. That's a bit of a spoiler.
Sorry.
Yeah, so let's say from this point of view, let's say the kind of line of thought that I've been presenting is that one could really start by looking at the classical expression, or let's say the metric and the connections, and simply try to generalize them by simply translating everything in terms of the natural ingredient that you have from the categorical structure. So essentially this T, then the evaluations and P. Maybe it's not the most natural way to proceed, but it's definitely a possibility. And it gives, as you see, very explicit formula. In particular, in the classical case, these two connections on the holomorphic and anti-holomorphic part, they reduce to the following expression, which again might not be very familiar because one will not really look at projective spaces from the point of view of this P, these generators Pij, but actually you can check that this is exactly what you get for the Levi-Civita connection acting on the cotangent bundle for these elements. So again, these are really checks that you can perform if you like using local expression in the classical case. So in a sense, this is also why I think it's nice to have these explicit expressions, because then you can really check things and compare it with the classical situation very nicely. Okay, then of course we can take the direct sum of them and obtain a connection of this complexified cotangent bundle. And as I said, the previous explicit formulae, they show that in the classical limit, this connection, nabla, reduces to the Levi-Civita connection on the cotangent bundle. Okay, so that's nice. So then nabla is definitely a good candidate to be a quantum Levi-Civita connection, according to the definition that I showed you before. Okay, so in particular, recall there are two flavors, let's say the weak one and the strong one. And we would like to check if then this connection is actually a Levi-Civita connection in that sense. Okay, so this we have not done yet. So then natural questions at this point are the following ones. Is nabla torsion free? Is nabla cotorsion free with respect to this quantum metric? Okay, so if we have these first two properties, then we can say that nabla is a weak quantum Levi-Civita connection. So that's nice. Provided we have that, then we can try to go a bit further and also ask, is nabla bimodule connection? Recall that's an extra assumption, an extra property that the connection might or might not satisfy. Okay, and if we are lucky and that is the case, then we can also check if nabla is quantum compatible with the metric. And that will give us strong or simply quantum Levi-Civita connection. Okay, so then let me cut the story a bit short and let's say we indeed check that the connection is torsion free and cotorsion free with respect to the metric. I guess as Ray was saying, this also follows from some more general results that I'm going to mention at the end. But of course, they can be checked concretely using this sort of expression and manipulation. Okay, so first of all, we get that nabla is indeed a weak quantum Levi-Civita connection. That is torsion-free, cotorsion-free. And as I said, in the classical limit, this reduces really to the Levi-Civita connection with respect to the Fubini-Study metric. Okay, so again, this is something you check from the concrete expression. Okay, so then this quantum metric compatibility holds in the weak sense, which is nice, but we can try to ask for more. So what about the strong version? Okay, so it indeed holds that the connection is a bimodule connection. And this, I must say, is probably the most technical part of all this result. This is something that I only added in the second version of this paper that I put on the archive, because it's just very involved, I must say. So it is not hard to guess what this generalized braiding should be, because, let's see, there is maybe a question. Oh yeah, bye Rita, nice to have you. So as I said, it's not hard to guess what this generalized braiding should be, because as I said, if it exists, it is uniquely determined by that condition of the definition, okay? But what is hard then is checking that this gives a well-defined bimodule map. So that is from omega tensor omega over the algebra to the same thing.
Sorry to interrupt you again, Marco, but how does this relate to the braiding in the category then?
Yeah, not in an obvious way. I don't think there's much one can say in general. I mean, of course, the expression use the braiding in the sense that, say, T here is some particular expression of R hat. So it involves the braiding, but there is no obvious way as far as I can see to just,
I mean, because these guys, these omegas, I mean, they're cotensor products. So I guess you could take the braiding on the U category of UQ of LFS modules and apply this.
I don't think that would work actually. I don't know. Perhaps, but maybe let me say something about this later.
Sure.
After I finish, let's say.
Well, then I have another small question. What do you mean by generalized braiding? Does it satisfy hexagonal?
No, not really. No. It's just a name that I think Beggs and Majid use for somehow. let's say it's really the property that lets you lift, as I said in the first part, a connection to a connection on the tensor product.
Okay.
So it is something that involves, in a sense, a right Leibniz rule for the connection. As far as I can see, it does not really have much to do with the hexagon equation and all that. It just says simply this map is the flip map, which would be the braiding. And so I guess that's all I can say about that. Yeah, so maybe let me cut this a bit short. Then indeed one checks that such a generalized braiding here exists and it does the job. So we get a bimodule connection. You see, we get this sort of complicated expression that involve all these complicated braidings acting in a complicated way. And in the classical case, of course, all of this very complicated mess just reduces to the flip map. Okay, so here there is really a lot of extra complication that comes from working in the quantum world, let's say. And also this, if you were to generalize this to, let's say, other flag manifolds, I think concretely it would look quite ugly, perhaps. So that's not great. Okay, finally, we have then a bimodule connection. We can look for metric compatibility in the strong sense. So we look then at this, as I was saying, this extended connection on the tensor product that acts on the quantum metric in this way. And we want to check whether this is zero. And indeed, this also turns out to be the case. And I must say this is easier than somehow checking that we have a generalized braiding. So this expression here vanishes. And then since our connection was torsion-free, then we get a quantum Levi-Civita connection also in the strong sense, which is really the best you can hope for in this setting, within this framework, of course. So therefore, in the case of quantum projective space, I think we obtain a very satisfactory picture, which is as close as possible to the classical one. And my conjecture would be that the same type of results then will hold more generally for all quantum irreducible flag manifolds. But of course, one might need more complicated ideas somehow to check that these things are true, perhaps avoiding concrete computations. I think one can go quite a long way with just general representation theoretic argument, but then some extra effort will be needed for some of the things. So just to conclude, because I guess maybe it seemed a bit unfair to a lot of other people that have worked on these things, let me just say how this compares to other results that were previously available in the literature. So for instance, we have this very nice recent result by a bunch of people that are here today, but probably not all of them, that shows the existence and uniqueness of covariant connections. So this extra adjective is important here, on quantum irreducible flag manifolds. And somehow this uses general representation theoretic ideas, and I think it's quite a nice result. Moreover, using the same line of thought, one can, for instance, also prove the fact that these connections, they are torsion-free. Again, using the same representation theory arguments. So moreover, even though I did not say really anything about covariant connection and I did not include the details in the paper, it turns out that these connections are indeed covariant. And so then this explicit connection then should also coincide, they have to coincide, with other connections that were introduced a while ago by Ray in a paper that was, let's say, concerned with the structure of these homogeneous spaces and, let's say, quantum Lie groups, let's say, in the setting of quantum principal bundles, let's say. So the motivation was somewhat different. And in particular, let's say in this paper, metric aspects are not explored. And so none of this metric compatibility, torsion, and all of that. But he introduced some connection, and it turns out that these are exactly the same as the one I introduced here, although maybe checking that concretely is not so obvious because conventions are notoriously hard, and also it was working with somehow explicit relations for the generators and all of that. Okay, but they're actually the same thing, which is nice, it's reassuring. Moreover, let me point out that in the paper by Majid that I mentioned in the first part, as I said, he had some of these results. So quantum metrics without invertibility, let's say, and weak quantum Levi-Civita connection, but he also had some other interesting results. For instance, he considers the Riemannian tensor corresponding to this connection. So let's say the curvature of these connections. And he defined things like the Ricci tensor. And he shows that a quantum analog of the Einstein condition holds, which means that this quantum metric is actually proportional to an appropriately defined Ricci tensor. So this is definitely, I think, an interesting thing to investigate within this more general setting. And my conjecture is actually that all this result, that is strong metric compatibility and so on, but also the Einstein condition, they're going to hold for general quantum irreducible Flag manifold. Although it might be quite hard somehow to prove all this stuff. So I think one needs a few better ideas to proceed along these lines. Okay, but I definitely stop here. I'm a bit over time, so thank you for your attention.
Okay, great. Thank you, Marco, and very much for a very nice talk. So we'll open up to questions from the audience.
Yeah. Can I ask a question? So I remember you mentioned before that Heckenberger and Cope proved that the connection is Levi-Civita in the weak sense, but not in the strong sense. And I think your result, they are in the strong sense. So, are these contradictory, or you are given a different connection?
No. So actually what I prove is that they are Levi-Civita in the weak sense and in the strong sense. So as I said, let's say a priori, these two conditions are a bit unrelated in the quantum world, but actually there is that extra, let's say, condition that lets you relate the two. That also turns to hold in this case. But let's say that computation I have not included in the paper that's on the archive, because somehow I came to those results in a slightly different way, let's say. But for instance, one could also show that that condition holds, and then strong implies weak in that case. But let's say in general, for a generic, let's say, quantum space, these two conditions might be unrelated. And so one might wish to explore them separately. Yeah.
Okay, more questions?
So what's the importance of the irreducibility of Flag manifold, of quantum Flag manifold? Is there any work on general partial Flag manifold or quantum partial Flag manifold?
No, in that case, I think things will be much, much harder. And, so my kind of philosophy, which I'm sure that Ray shares, is that one should really approach these things somehow layer by layer, starting from the easiest possible case that perhaps not very intuitively, because you might not expect that this class of homogeneous spaces is really, let's say, the nicest one, but it turns out to be the case for various reasons. Of course, one could go, let's say, all the way up to the compact quantum groups, for instance. And it turns out these are much more complicated. So let me just mention one thing. I said, for instance, for these irreducible Flag manifolds, there is this nice classification of differential calculi. There's basically only two, and they are as close as possible to the classical case. So you really pretty much translate all the properties that the RAM complex has to the quantum world. Now, as soon as you step already into the world of the 3th sphere, so SU2, okay, then already you have a lot of differential calculi, and it's not clear which one to choose. Moreover, there are different competing notions. For instance, one could ask for left covariance and right covariance that gives rise to this notion of bicovariance. And if you ask for that, then, for instance, you cannot have a calculus of classical dimension, which you might just accept as something that, okay, that's just how it works, just how life is. But I think for various reasons, one might need to modify that condition a little bit and instead work just with left covariant calculi and somehow maybe with some twisted version of right covariance. But then as soon as you step into left covariant calculi, there's a lot. And then it's not clear which one to pick. So I think there's still a lot of work to be done there. Also, I would expect that things like quantum metrics in this very strong sense, they might actually not exist, perhaps. So one might need a weaker property of, let's say, quantum metric. And also all this strong stuff might not hold. So it's really a much more complicated world. So this is why the irreducible case is really nice, because everything works, let's say, as in the classical case. So that's really the starting point. And my point of view is that first one could try to settle this more or less completely for all these irreducible flag manifolds, and then try to increase the complexity a little bit. And so the next step would actually be these U1 bundles over these irreducible flag manifolds. So for instance, the spheres, they would appear as these U1 bundles over the projective spaces. So that would be, in a sense, the next step. Mm-hmm. I think that should be manageable, but again, new ideas will be needed. And there certainly will not be any uniqueness, so one has to make perhaps some choices, and which choices? Well, we'll see. We hope there is a natural one at the end of the day, otherwise it's a bit unsatisfactory. But we have to start somewhere, let's say.
Yeah, so I have been, well, since myself and Peter are here, we've been doing some work on the full flag manifolds actually, yeah. And there it seems that there are actually calculi as well, and just two. This is still very much work in progress that was interrupted by the pandemic and teaching.
Okay, so you mean two satisfying which properties?
Classical dimension, I guess. Yeah.
That doesn't seem possible, because there is a classification by Heckenberger actually about the left covariant on SU2, which would be...
No, not on SU2, on the full flags, on the full flag of SU3, SU4, and so on.
Okay, so not all full flags. Because I mean, you know, SU2 would be then the full flag corresponding to the two sphere.
No, the Padlish will be the full flag corresponding to SU2.
All right, yeah, sorry, I said something stupid.
So
right.
it's the same space that Bob was working. Yeah, no worries. But the one that Bob was working for SU3, for example, they seem to have calculi. But I probably shouldn't say any more because, yeah, it's the draft is still in.
Yeah, I mean, so my intuition would be that somehow there is, in a sense, this extra generator, this K omega S, so the root you remove.
Yeah.
If you look at that from the point of view of quantum tangent spaces. And so somehow you simply need to insert that extra generator. But
sure,
then
sure.
Yeah, but then I would expect that you still have the choice of a power of that element.
But then you don't need to know, because you're, I think, no, maybe I'll discuss this with you in person. I should probably not. Sure. It's definitely work in progress, so it's probably not the place to. Sure. However, I do have questions.
Yep.
Okay, so this one I did. Yeah, most of the question was because we've been approaching it from a different point of view, from the point of view of Chern connections. And there, I guess the ones that you said were easy or easier were also easier for us. But the thing that was the hardest for you, we couldn't do at all, which is to say the bimodule connection.
Yeah.
So it makes sense. It makes perfect sense that this was, because we could prove it using the Voronowicz calculus for the Padlish sphere, and that was interesting. But then my question about this is, do you have any ideas for how the curvature of the connection would relate to the bimodule?
To the bimodule?
Yeah, so you apply the curvature twice and you're going to get some sort of curvature. You'd like to calculate it. Of course, this is very difficult.
Yeah, sure. I mean, you would have the same decomposition, let's say, as the Chern connection. Actually, those are computations I already made, but they are still not available. Because I wanted to get a bit further and also prove that one has this Einstein condition. And so that requires a bit more effort. But yeah, I mean, basically by your general results, you would have this, right?
Yeah, maybe.
Because it's just that there's no, let's say, invariant elements in the appropriate, let's say, home spaces.
Yeah, sure.
So
But I guess maybe I was asking a slightly different question. So I guess what I was interested, so maybe I should ask a preliminary question first. You were looking to show that omega 1 or omega plus, omega minus, that these have bimodular, that it was a bimodular connection for these guys. So what about for line bundles, something easier?
Yeah, I guess this is already known, probably.
If it is
a paper by Landi, Van Silicon, right?
Maybe for Padlish, but that's it, I'd say.
Yeah, I'm pretty sure for Padlish, yes. For projective spaces, I don't think so. Maybe.
Because I mean, for Padlish, the line bundles are going to coincide with omega plus and minus, well, more or less up to.
You know, actually checking that for the line bundle, I think it's very easy.
Okay, that would, if you can do it, if you could point me in the
I
direction.
mean, maybe depending on the picture you start from, but it should be easy. I mean, I don't know. I will need to look at that, but I seem to remember looking at this computation, let's say by Landi and these other people for the Podler sphere, and checking the bimodule condition was extremely easy there. Okay. It was just a very simple computation.
And then you would guess that the extension. So then I guess the thing that happens with these when you calculate, I calculated the curvature explicitly using a different method. What you get is that if you have, let's say you take E1 and you tensor it with E1 and you calculate the curvature, classically it's additive, so you're going to get 2 by the Kähler form. So the curvature of E1 tensor E or EK tensor EL is going to be the sum of the curvature of the first plus the curvature of the second. A classical differential geometry.
Yeah, I don't know.
Curvature is additive over tensor products. And then what happens in the non-commutative setting is that, let's say for Padlish or for higher CPN, it turns out that instead of getting integers in this way, you get quantum integers. So the addition, the additivity over tensor products becomes Q-deformed. I guess this should have something to do with the bimodular, but I can't.
Yeah, possibly. I mean, let's say also here, of course, there's a lot of Q numbers lurking beneath the surface. So for instance, just to mention one thing, there is also this notional dimension of a differential calculus, not, let's say, in the usual sense, but something defined by Majid, I believe, where you apply then this, you essentially compose the quantum metric with this bimodule map, the inverse metric. So classically, this simply gives the dimension of the tangent space. And so this also essentially gives a scalar in this quantum setting, and that should be again some Q number of.
So it's like a version of, for the metrics, it's a version of the quantum dimension in the.
Yeah, although I don't think it's really the quantum dimension though.
But it's the same ideas, no?
Same ideas, but maybe something slightly different. I mean.
Okay. Yeah, the last thing was just a comment though with the Chern connection. There's also, for the Chern connection, there's a notion of metric compatibility, which somehow you get almost by construction, because you start off with the holomorphic structure, then you impose a metric, and you know by general results that you have a 1, 0, and then you get the connection. And by construction, it's metric compatible. Maybe that would be a way, if you could, it's an interesting question to see if the metric compatibility of the Levi-Civita and of the Chern are the same. But then since they were produced by Majid.
But the metric compatibility is a bit different, right? For instance, you don't need to have a bimodule connection to have that.
No. So it's, the relation between them is not clear to me, but it would be interesting to try to see how or if they relate.
You know, I know what you mean, but I don't really know what is the connection, the relation between the two, let's say. But surely there is something there. I mean, but I don't know.
Okay, but though, if you do ever write down that the line bundles, that the connections for the line bundles over projective space are bimodular connections, I would like to see it.
Okay. I need to take a look at the previous computation and see if they cannot be adapted, I guess, but should be possible, I think.
Okay. Great.
Well,
so are there any other questions?
yes.
Yeah.
Then I have a final question about that generalized braiding give you bimodular connection. Is it at least symmetrical? So is it square equal to identity?
No, surely not.
Okay. So it's not unitary part of the braiding in the UQFG modules?
No. It definitely, I said, if you look at the form, it's much more complicated than the braiding. If you just were to consider, let's say, the braiding between this simple module B that I consider and its dual, or B and B, that is much easier. That would be essentially the action of just one braiding. While here, basically, well, of course, as let's say 4 indices, so really you are kind of moving 2 copies past 2 copies, but it's even just not that.
But why I'm asking, it's remind me this unitarized braiding as defined by, I don't know, Greenfield.
Sure.
And which is constructed from a braiding. It's not a braiding anymore. It's some symmetric commutativity constraint, but it gives you square. And yes, it's, what is it? It's a braiding square root of.
You divide by the square root, yes. But that's a kind of a different beast, really, because it is symmetric, but then you don't have anything like the braid equation. So you have
no. It's a cactus relation.
Exactly, the cactus relation, these co-boundary categories.
But still, it gives you, for example, Heckenberger and Cole calculus as a quantum exterior algebra of corresponding modules.
Okay. In the sense that you consider something like Nichols algebra related to that.
There is this Bernstein-Zwinz-Nagel quantum exterior algebra.
Yeah, sure.
So in this sense.
Yeah, but okay, in that sense, yes, of course. No, that's exactly the same as this Heckenberger-Kopp stuff. It's really the same. They give rise to the same exterior algebra.
Okay, thanks.
I mean, actually, if you look, say, at the Berenstein, actually in the Zwick-Nagel paper, it's not mentioning the Berenstein-Zwick-Nagel paper, they say that all these quantization were previously obtained by Heckenberger and Kolb. They're exactly the same thing.
Yeah, Berenstein, he was Zwitznagel PhD supervisor.
Yeah.
And then Zwitznagel left us.
Yeah, I mean, because at the end of the day, also Heckenberger-Kolb really look at, let's say, the positive signs, let's say the positive eigenvalues and the negative eigenvalues. So it's really the same thing. Just that they have systematized a bit more and they show that there's a couple more examples, but in particular, they show that all the flat, at least Zwick-Nagel show that all the flat deformation are pretty much just those coming from irreducible flag manifolds, plus a couple more that are related to some Heisenberg stuff, something like that.
Well, it's the Poisson structures on the
Yeah, but it's very special Poisson structure, right?
Yeah, I know that paper in advances.
Yeah, exactly.
Thanks.
Okay, so are there any more questions, or have we yeah, okay, so I think that's it. So thank you again for a very nice talk, Marco.
Thank you.
And so, as I said, that's the last talk of the year. So we'll resume again in January 2021, the 12th of January, when Branimir Cacic from the University of New Brunswick will speak. The title will be coming later on. And yeah, so I guess we wish you all a happy Christmas and hope to see you again in January.